There is a conjectured relation that physics say hold very broadly. Irrespective of the dimension, these are related by this identity, chi equal to twice psi minus 1. Okay. And actually, independent of the model, also in some sense, all kinds of models like this should satisfy this relation. So there must be some general principle behind it. These were conjectured in numerous physics papers, starting from the mid-80s to the early 90s. And due to its appearance in this paper, famous paper of Kardar, Parisi, and Zhang, it's sometimes called the KPZ relation. The rigorous literature gives some support in one direction. Newman and Pisa showed that chi prime is bigger than twice psi minus 1, where chi prime is a related exponent. It's probably equal to chi. And there is an earlier result of Ware and Eisenman who proved another similar relation like this. Chi is bigger than or equal to 1 minus. So it's dimension dependent, this inequality. There is something else which is called Brownian motion in a truncated Poissonian potential. So it's one of Alan Snitman's models. Here Wootrich, who's a student of Snitman, was able to prove the opposite inequality. But it's a different model. It's different. It's supposed to be related, but the relation is not quite known. So in this talk, I will prove this relation that chi equal to twice psi minus 1, assuming that the exponent exists. So that's the purpose of the talk. That in quite generality, this relation holds, assuming that in a certain sense, the exponents exist.
So you could just define the exponent the way you did, though, right? Then that's not good enough.
That's not good enough. So for the proof, that's not good enough for the proof. In particular, it's not clear whether, in some sense, it's not clear whether that's the right definition either, because, infimum where it's tight, the smallest value where it's tight, maybe it's because it's the smallest value because there is some direction in which it's, order of that, but in other directions it's less. It's less. So you have to assume from the other direction from below also. So somehow to say that an exponent exists, it has to be the same in all directions. So direction independence is important. Okay, so I'll now define in what sense. So you have to define both from above and below. So there is this notion of exponential tightness. So we have to assume something stronger for the purpose of the proof. So recall that a family of random variables is said to be exponentially tight if there is an alpha, so that e to the alpha absolute value of xn is uniformly bounded as n varies. Okay, so this is stronger than ordinary tightness. It says there is a uniformly bounded exponential moment. What Keston proved in 1993 is that chi less than or equal to half, in the sense that this family is exponentially tight. Not only is it tight, this is exponentially tight. So that's under some assumption on the distribution of the random variable. So you assume that the edge weights themselves have exponential moments and so on. Keston proved that this is exponentially tight. Okay, so inspired by this result,
any dimension again.
Any dimension. So it's a concentration result. It's basically a concentration inequality. What he proved using martingales. So inspired by this result, one can define chi a. So a for above. So chi a to be the exponent, to be the infimum delta, the smallest delta, so that this family is exponentially tight. Okay, so that's the definition of the exponent from above, and the demand is that it should match with an exponent from below. In which case, I say that the exponent exists. Okay, so is this definition clear?
So all you have to do is replace tight by exponentially tight, and then that's good?
Yeah. So no, but one more thing. So it has to match. So I said just from above. Okay. Okay. So it is easy to show under mild assumptions that there is a positive constant, so the variance is bigger than this constant for all x, y. So as before, you can define an exponent from below so that the variance is bigger than t times x minus y to the 2 delta for all x, y. Okay. So this is the definition of the exponent from below. So that if delta is indeed the right exponent, then this should be satisfied. So you take the largest delta so that this is true. Okay. Okay, and similarly, okay.
You really want it as an equality? Oh, I see. It's not probabilistic anymore. It's just a variance.
Yeah, it's just a variance. Yeah. Okay. So at least there is some delta. This shows that delta equal to 0 works, but you take the largest delta so that this is true. And if the exponent exists, then of course you would expect it to satisfy this, just as you might expect the other way. So one can show with not much difficulty that chi b, this exponent from below, is bigger than 0, is less than chi a, and chi a is less than a half by Keston's result. So you can prove all this. And we'll say that when chi a equals chi b, then the fluctuation exponent exists and equals this number. Okay. So that's the definition of the exponent. If they are equal, then the exponent exists. Okay. And the wandering exponent, the transverse fluctuation exponent, may be defined in a similar manner by defining from above and below and saying that it exists. So I'll skip the definition. Again, matching. So what this definition is about, it's basically about direction independence. That's what it's about. That if you have in a certain direction the fluctuations are of order much smaller than in another direction, then this will not happen. Okay, because the exponent from below will catch the direction of smallest fluctuations, and the exponent from above will catch the direction of largest fluctuations. Okay, so saying that they're equal is saying basically that it's direction.
Some isotropy here, right?
Yeah, yeah, that's
long distances or something.
yeah. So you expect unless the distribution of the edge weights is something very weird, you expect things to work. Okay.
So you're not making any assumptions about the typical speed of propagation, the dependence of this on the direction?
I am not making any assumptions directly, but the existence of these exponents may have some inbuilt assumptions in there. So I suspect that there is some assumption inbuilt into the when I'm assuming that the.
So does this imply some strict convexity?
I think it should. I haven't tried to prove that, but I think it should. The strict convexity. So there is actually some evidence that it should imply that. There is one other thing that I need, which is something about the distribution of the edge weights. So it follows from Keston's result that the variance of txy is bounded by the distance between x and y. And for binary edge weights, when the edge weights are just two values, a and b, this was improved by Benjamin Nicolai and Schramm, who used this hypercontractive inequality to prove that you get a logarithmic improvement. So it's a big open question in percolation, first passage percolation, whether you can replace the exponent 1 here with something less than 1. So they couldn't quite get that, but they improved by a log factor. And we will say that the edge weight distribution belongs to the BKS class if this above improved bound holds, and this, so 2-point distributions belong to the BKS class, but more recently it has been proved that a large class of distributions, including exponential, beta, gamma, uniform distributions, all belong to the BKS class. That is, you can get logarithmic improvements. So I'll need that.
So the original proof uses the binary.
Yeah, yeah.
Use that.
Yeah, so
now people have gotten away from that.
yes. So well, throughout I'll be assuming a continuous distribution, so I cannot use this result directly, but recently, people have gotten away from that, and
So in two dimensions, one expects that to be what, x minus y to 1/3? Is that right?
2/3.
Two.
Yeah. So the fluctuations are 1/3. So the variance is 2/3.
the other way.
No, the variance is, the variance of t is of the order x minus y to the 2/3. That's what they think. That is the standard deviation of txy is of the order x minus y to the 1/3.
Yes. Oh, so
Yeah.
that's 1/3 there. Because you have a less than x minus. You're saying that's 2/3.
Because it's a variance.
The variance is the square of the square. Okay, so this is a nice result. They extend this paper to these distributions, and a large class of distributions. But it's still, I think it should hold for an even larger class. I think everything satisfying a log Sobolev inequalities probably should be okay. So here is the theorem. Consider first passage percolation in any dimension bigger than or equal to 2. Suppose that the edge weight distribution is continuous and belongs to the BKS class, and that the exponents chi and psi exist in the sense defined before, okay, then you have this result. Okay, so that's the theorem.
Is it dependent on the dimension?
No, this is a dimension-independent result.
And you don't need, see, the edge weight distribution continues, but you use some independence too.
Oh yeah. So first passage percolation meaning that IID. Yeah. Okay, so I'm just
But presumably it works under milder conditions too, right?
presumably, yeah. I'm not using the independence in a big way. It's just the results that are available. So I'm using that. And there is a further good news, which is recently in a paper of Finger and Damron, they have made an important progress which removes this BKS assumption, and the proof is nicer. So I'll talk more about it later. So okay. Okay. Any questions?
So it's actually true without the BKS assumption.
Yeah. But chi and psi are the same. So you assume that the exponents exist in the same sense, and then you have this. And you have to assume that exponential moments on the edge weights, that's inbuilt into the chi and psi, the definition of chi and psi. Okay. So let me go into the sketch of the proof directly. So the first step, you consider the expected passage time from 0 to x. Define that function hx. That's a function on integers. And this function is subadditive. That's not difficult to see. And then therefore this limit for any x, if you define h nx over n as n tends to infinity, this exists. So you define that to be gx. This gx is again a function on the lattice. And this can be extended to all rational numbers by taking n to infinity through a subsequence where these are integers. And finally can be extended to all of Rd by uniform continuity. So this h gives rise to this function g. And it's very standard, something that people do in first passage percolation. And the idea of defining this function is that for large x, gx and hx are approximately the same. So g is a nice function. It's actually a norm. Okay, the function g is a norm on Rd, and for large x, gx and hx are approximately the same. So that's the idea. So this expected passage time can be approximated by a nicely behaving norm on Euclidean space. Okay, so that's the first step. Okay, is the definition of G okay? Okay, so first define on integers, then on rationals by taking n through a subsequence, and then to all of the space by uniform continuity. You can prove that it's uniformly continuous. So G is a norm, and this is much more well behaved than this h, the expected passage time. And if x is a large point far away from 0, then this is supposed to be a good approximation. And there is this very useful method of Ken Alexander. So you try to bound this. So typically, when you have a subadditive, when you use a subadditive lemma, you don't know the rate of convergence. Okay, but in this particular case, you can use the independence of the random variables to get a rate of convergence. So there is something in percolation called this BK inequalities, Vandenberg-Keston inequalities, which help you to go the other way, and that's basically some very sophisticated version of that. Ken Alexander uses that, and what he proves is that the error is x to the half. But in my paper, that argument can be reworked actually with the definition of the exponent that I have. If chi is the exponent in the way that I defined, then you can prove that g approximates h up to order x to the chi. Okay, for any there's a little error. So this g and h are so this is very important that you get this error, and this comes from this method. So that was
What is h of x?
h of x was the expected passage time from 0 to x. Yeah, and gx is the approximation. Okay, so then you have this bound where chi is the exponent. So it's essentially x to the chi. Okay, so you can have this this approximation, which is quite fundamental. So in the proof of the main result, so in the theorem, this approximation will allow us to replace hx by gx everywhere. So we couldn't do this if we had a cruder approximation. So this Alexander's theorem is very crucial. This approximation allows you to actually do that.
So the main ingredient of Alexander's method is this Vandenberg-Keston?
It's not Vandenberg-Keston. It's a much sophisticated version of that. So Vandenberg-Keston will be only for ordinary bond percolation or percolation like that, but he uses something along similar lines developed for first passage percolation. So
can you say anything? I don't know much about this. Can you say a little bit about that, or is that
no, it's very complicated.
okay?
It's yeah, it's very complicated. Okay. So of course this side is trivial. This is directly from subadditive lemma, but this is the difficult side. Okay. Now one last thing I need about this g, this norm g, is curvature lemma. So it's basically, it says that there is a direction along which you consider the unit ball of g. G is a norm, so g has a unit ball. The unit ball, there is one direction where it's at most as curved as a sphere, and there is another direction where it's at least as curved as a sphere. So in the direction x0 here, the unit sphere of the norm g is at most as curved as a Euclidean sphere, so it satisfies this. This is the tangent hyperplane. So if you go along that hyperplane, you deviate by at most z squared. And there is another direction where it's at least as curved as a Euclidean sphere, so that if you go along a tangent hyperplane, you get at least distance z squared away from it. So that's easy to see. Given any norm, nothing special about g. Given any norm, you take the unit ball. There is one direction where the curvature is, it's more at least as curved as a sphere, and there is another direction where the curvature is at most as curved as a sphere. It's just by shrinking spheres from above and expanding spheres from below. So you prove that they will touch. Okay, so this is again another important observation that this happens. That there is in one direction you have g of x0 plus z goes like, the error goes like z squared, at most z squared. Another direction error goes like at least z squared. So as soon as you have this, it's very easy to sketch a proof of one side of the inequality, the side that was already known from the work of Newman and Pisa, chi bigger than or equal to twice psi minus 1. Okay, so I can directly sketch it now. Okay, so, and the proof is by contradiction. You assume it's strictly less, and then you get a contradiction. So by this direction of curvature where it's curved more than a sphere, the expected passage time of this path, so let's say there is a path from 0 to this nx1 going through a point mx1 plus z. Z is this deviation. So the expected passage time is at least this passage time plus this passage time plus whatever error you get. So this is from Alexander's approximation. So you get these two things, and then you use the deviation, the curvature lemma. So what you eventually get, if you do the computation, you get that the time for this path that passes through this point over here is bigger than the unrestricted time plus an error of z squared over n plus some error of n to the chi, okay, z squared over n. So if z is n to the psi, this is the fluctuation, the transverse exponent n to the psi, then this is n to the 2 psi minus 1. So what happens is that if 2 psi minus 1 is bigger than chi, then this cannot be a geodesic, because the expectation, the amount of increase in expectation of the passage time will dominate the fluctuation, okay, and therefore you cannot have that this is the geodesic. That is, you know, the length of this path in the actual model is the expected plus the fluctuation, and the fluctuation will be much less than the error that you get from the expectation. Okay, so that's the idea. That's very simple. It's just that if this condition doesn't hold, if indeed twice psi minus 1 is bigger than chi, then a path that goes n to the psi away from the straight line, the expected passage time through that path is too large. Okay, so the fluctuations would not be able to kill it, so that cannot be the optimum path. Okay, and then you have to somehow combine over all paths and so on. But it's too large. The expected passage time is too large. So if chi is less than twice psi minus 1, you take a path which deviates by n to the psi. Okay, you take any path which deviates by more than n to the psi from this.
You are trying to prove that the path will not deviate that much.
Yeah. Yes. So it cannot deviate that much, and it gives a contradiction to the definition of psi.
Now, in this result of Alexander, which you said the proof is complicated,
yeah,
does he assume for that result? Do you have to assume one of the stronger senses that you had of the meaning of the exponent?
Yes. We must assume that. So what Alexander proved is that the error of order n to the half, because he already had that from Keston's result, that the stronger exponential bound. So I tried to drop the exponential bound, but you really cannot. I mean, somehow it's strictly required for that proof to go through.
So basically you are saying you are comparing the actual with the expected value, and
Yeah.
the difference is the expected value of the fluctuation.
Yeah.
And somebody wants to know that the very large fluctuations do not bias it.
Sure. Okay. So again, this error that you get is from this bound. From this bound over here, this is the bound that gives you this error, and then you say that if n to the the increase in expectation of passage time is n to the twice psi minus 1, and if this is bigger than chi, then p cannot be a geodesic, because the fluctuations of p will not be able to bring down the passage time to the level where it's feasible to see it as a geodesic. Okay, so that's the.
I'm missing the key point here. Are you using somewhere the effect of the changing the angle on h of x?
Yes.
Where is that?
Yes. So okay. Okay. So let me see. So for this, so you assume this, and to arrive at a contradiction, you have to assume that the path deviates by at least n to the psi. So you have to know that the path deviates by at least n to the psi. So yes, so this is a direction where the path deviates by at least n to the psi, and in the other inequality, I'll have to use a direction where the path deviates at most n to the psi, and those two psi's should be the same. Okay. So for this proof, for this one to go through, you strictly don't need the direction, that it's the same in all directions. So for this proof, you don't need that.
be able to apply this Alexander lemma.
Oh yeah, right, exactly.
Without using the-
Okay, that's true. So to use Alexander's lemma, this error, so you assume the exponent is the same. But that Alexander's lemma works with chi a. I mean, you can prove it with the exponent from above. So that's not a problem. So in my paper, what I prove is that actually chi a is bigger than twice psi b minus 1. That's it. So chi a is the exponent from above. That's well defined. Psi b is the exponent from below for psi. That's also well defined. And I prove that chi a is bigger than or equal to twice psi b minus 1. That's what I prove. Yeah, so you don't really need that. Other questions? Okay, so this is an old idea from Newman and Pisa. It's just putting it into these definitions, you can get this result. Okay, so proving that chi is less than or equal to twice psi minus 1 and chi is positive. So there are two cases, chi positive and chi 0, and the proofs are completely different, but I'll show you only this case, chi is positive. So what I do is the following. You have 0 to this point n times x0. Okay, x0 is the direction of curvature defined before, and you subdivide into little blocks of size a x0. Okay, 0 to a x0, twice a x0, thrice a x0, and so on. Okay, so the solid curve is the geodesic from 0 to nx0, and the dashed curves are these little geodesics from these points. And this a is n to the beta for some beta less than 1. Okay, and m is the number of blocks, n to the 1 minus beta. So what I will show is that under this condition, chi bigger than twice psi minus 1, so I'll get a contradiction. Again, the proof is by contradiction. So if chi is bigger than twice psi minus 1, we'll show that there is a beta, so that the total passage time from 0 to nx0 is approximately the sum of these individual passage times plus something that's much smaller than the order of fluctuations. Okay, so that'll be the key step, this star. I'll show that under the assumption that chi is strictly bigger than twice psi minus 1, this total passage time for some appropriate beta less than 1, this total passage time is the sum of these individual passage times plus little o of n to the chi. Okay. Okay. So this will give a contradiction, and I'll show how it will give a contradiction on the next slide. There is a beta parameter, implicit here. So m is n to the 1 minus beta. So there are m blocks. There are m blocks, and each of length n to the beta. Okay. Total passage time is the sum of these individual passage times. Okay, so how do you get a contradiction? So let fn be the variance of t n x0, and by the BKS criterion, fn is bounded by some constant n over log n. By the FKG-Harris inequality, the variance of t n x0, it's the variance of the sum of these individual times, and that's bigger than the sum of the variances. So variance of a sum is bigger than sum of the variances, since you have the FKG-Harris inequality, positive correlations. So this is n to the 1 minus beta times f of n to the beta plus little o of n to the 2 chi. And this error is too small. Okay, so the error is too small. So essentially this equals this. And what this shows is that fn over n to the 1 minus beta times f of n to the beta lim inf is bigger than or equal to 1. Okay. And this cannot happen under this condition. If a function satisfies this, it cannot satisfy this. Yes?
Where do you get this small o of n to the power 2?
Yeah, so this is,
Where do you get this from?
yeah, from this star, which I haven't proved. Okay, so the total passage time from 0 to n is the sum of individual passage times plus a little error, which is little enough to be ignored. Okay, and I'll show this, and then that gives you this, which shows this inequality for some beta strictly less than 1, and that cannot happen under this condition. And why cannot it happen? So you just take some n0 and define ni recursively, sequentially like this, ni to the 1 over beta. Let vn equals fn. It's a small analytic exercise. Vn equal to fn over n. Then vni is less than this, c to the beta c times beta to the I by this inequality. And but you also have this from this. So for all I large enough, this is bigger than beta to the half v ni. So you get v of ni bigger than constant beta to the I over 2, and which gives a contradiction. These two things together give a contradiction. So essentially this is, you know, a little exercise, but the main thing is that this and this are not compatible. Okay. So this cannot hold. That is, I mean, intuitively it's also clear that if if the passage time is indeed a sum of little things, then its variance should grow linearly. Okay, it cannot grow like n over log n.
Can you remind me what's star?
Oh, star is this, that the passage time from 0 to n times x0 is the sum of these individual passage times plus a little error. Okay, and that I prove under this assumption. So ultimately we get a contradiction showing that this is okay. Any questions?
Back to, did Newman and Pisa use the same argument that you used?
So Newman and Pisa proved the other inequality. So yeah. Yeah. So this is the same argument. It's essentially it's the same idea. Yeah. Okay. So we have this, and let's now try to prove this star, this thing over here. Okay. So what you do is you break up this. You take 0 to nx0, you do a cylinder of width n to the xi, so that the path essentially lies within this. And you break into small and big blocks. Okay, so what you do is a is n to the beta and b is n to the beta prime, where beta prime is even less than beta. So these are small blocks, these are big blocks, and you define these partitions as these walls as u0, v0, u1, v1, etc. Okay.
Those are deterministic, right?
Deterministic, yeah. And then, so you partition to big and small cylinders, and the boundary walls of the cylinders are these. So since beta is less than beta prime, beta prime is less than beta, these are negligible parts. So there are basically n to the 1 minus beta blocks. Okay. So then the key step, okay, I used to give the proof of this in earlier lectures, but it always confuses people, so I am skipping this. This is simple logical argument. Okay, there is nothing, nothing probability involved in this. The passage time from this wall to this wall, you can consider passage from point to point, but you also consider passage from wall to wall. It's essentially the same. The passage time from u0 to um is approximated by the individual sum of the individual passage times. So these are the passage times across the big blocks, these are the passage times across the small blocks. And the key thing is this difference is bounded by the sum, where the sum is only in the small blocks. So errors come only from the small blocks. So the error is mi, the error from the ith small block is this. So you consider a point v and v prime on the left wall, and u prime on the right wall, and you take t vu, one passage time, and the other v prime u prime, and then maximize over all possible choices. So it's using the definition of passage time, somehow you can you can do a logical argument to show that the total passage time minus all the individual passage times can be bounded only by errors coming from the small blocks. Okay, so you don't have to involve the large blocks. I mean, you can also bound it by, it's just a question of alternating blocks. Small and large doesn't matter here. If you have alternating blocks, then the total passage time minus the sum of the individual things can be bounded by errors coming only from, let's say, the even numbered blocks. Okay, you don't have to involve the odd numbered blocks. So what is the advantage? Okay, but first, any question?
How have you chosen those blocks so that's useful then?
Yeah, so that's in the next slide. So beta prime less than beta less than 1, how do you choose those? So by the curvature estimate in this direction, So now I'm trying to estimate this thing, that is the maximum difference between two passage times, you know. So you have this is a small block. So you have one path, you have another path, and you want to bound the difference between these two times. So the first step is to bound the difference in expectation and then fluctuations. Okay. So the expectation difference, you know, you can, you know, by the curvature estimate, you can take my word for it. It's the estimate is n to the twice psi minus beta prime. So instead of 1, you have beta prime. And the fluctuations are of order n to the beta prime chi, because the length is beta prime. So the fluctuations are of order n to the beta prime chi. So if twice psi minus 1 is strictly less than chi, you can choose beta prime sufficiently close to 1 so that this term is dominated by this term. So that the expectation difference is dominated by the fluctuations. Okay. So when you're trying to estimate the difference between these two times, there is an expectation difference, there is a fluctuation. And the fluctuation dominates if beta prime is chosen sufficiently close to 1 under this assumption. Okay. If beta prime is sufficiently close to 1, then you can make this less and the fluctuations dominate. So mi will be of the order n to the beta prime chi. And therefore, the total error will be n to the 1 minus beta plus beta prime chi. Okay.
Are you using independence?
No, I'm not using independence. So you see, this is an absolute error. Okay, this is an absolute error. There is nothing probabilistic about this. Okay, and then when you're trying to bound this, you know, so the total error is just I'm adding up these things. I'm just adding up. So that there are n to the 1 minus beta of those, and I'm adding them up, each of size n to the beta prime chi. So we have this. So since beta prime is less than beta and chi is positive, you know, you can choose these things so that this total error that you get is less than chi. And that was our star. So in star, we use that the error is n much less than n to the chi. And that's what allows us to the whole argument to go through. Okay. So that's why you have the small block and big block construction.
Can you go again over this lemma which you do not want to prove?
Yeah.
Small blocks provided bound. I mean, what if the small blocks are taken to be of order 1?
That's what really that was wondering about too.
No, you.
It's very large.
No, but you can take the small blocks. You know. You know.
Can you leave it just again? For small
Okay.
blocks, you're adding what? Sorry, what happens if the small blocks are of size 1, of width 1?
So. Yes. Okay. Okay. So if the small blocks are of width 1, then you know it's just one wall. Then you know it's all paths from the wall has many points. So you can consider paths from one point to the other along the wall. So you know you'll get something non-zero, and it'll be much worse than a big block. Okay. So you have to take beta prime close to 1.
You get worse error.
You get worser as you take small blocks.
Okay.
You get worser.
But to do your argument, estimating the difference between passage times here, we need the cylinder to be thin. So we need.
Yes, we need. Yes, we need it to be thin. So somehow, but anyway, so this whole idea of taking the cylinder and adding up over small cylinders, this comes from this earlier work I did with Partha Dev, who was my student at Berkeley. Is for proving central limit theorems for passage time across thin cylinders, where we broke this up. So initially we had this scheme of breaking up into just walls, okay. But then it occurred to me that if you take the small blocks, then you get a much better estimate than if you just do walls, okay. So somehow there are some cancellations which happen. Okay, so this is of this order, and therefore you get this, and chi is positive, so you can choose this beta and beta prime less than beta, so that this whole exponent is strictly less than chi, and this will prove the star. And here, coming back to the theorem of of Inger and Damron, is that this this passage across small blocks. So it turns out that you can actually use this, just this idea, to actually get to a proof without using the whole scheme of breaking into cylinders. You can use this to get this bound when chi is positive. And I think Michael will talk about this later sometime here. Yeah, this is a very nice proof, and I think that's sort of the right proof, and my proof is not quite the right proof. But so this is for chi bigger than 0. Okay. Any questions? Okay, and for chi equal to 0, I'll not tell you. It's actually, I like this proof better, but I'll not go into that. And just a digression. So actually, Michael asked me to talk about concentration and these things in this phenomenon. So I just put this slide in. So it is conjectured that chi equals 1/3 and psi equals 2/3 in 2 dimensions. It is also believed that chi may be 0 in sufficiently high dimension. That's all unproven. Keston showed that chi is less than or equal to half in any dimension. Now, it's not known whether chi is strictly less than half. People believe that. People think in 2 and higher dimension, chi is strictly less than half. And this phenomenon is sometimes called sublinear variance. So I call it super concentration in my paper. So there is a reason for that. I mean, it's going beyond ordinary concentration of measure. So it's basically is the regime beyond whatever you can get from ordinary concentration of measure. And it manifests itself in many other models. And in the related model of last passage percolation with Gaussian weights, so where you have Gaussian edge weights and you take the maximum path instead of the minimum, I proved that, essentially, so you'll not see it in this form in my paper, that chi equals half of tau, where tau is an exponent such that the size of p intersection p prime is of the order n to the tau, where p is the optimal path and p prime is the optimal path in a slightly perturbed environment. Okay, so you take the optimal path and you take, so I'll not tell you what is meant by a slightly perturbed environment. So you perturb the environment a little and you get a new optimal path, and then the intersection of these two paths of length n is of the order n to the tau. So this is the exponent. So chi is half tau essentially. And in other words, chi is less than half if and only if tau is less than 1. So the phenomenon tau is less than 1, meaning that the two paths don't intersect too much. If tau is 1, then they're intersecting on a macroscopic level. If tau is less than 1, it's sometimes called chaos or disordered chaos in these systems. So the main result is that superconcentration is equivalent to chaos. So that's and this may be one approach of trying to prove this actually. So that proving that with a perturbed environment you get an optimal path which is very different from the original path.
What does it mean, slightly perturbed environment?
Yes. So in the Gaussian case, what I do is I take each variable, each edge, and let it flow along an Ornstein-Uhlenbeck flow. So you basically you take a Gaussian variable x, and you take an independent Gaussian y, and you take ax plus by, where a squared plus b squared is 1. So if a is close to 1, okay, for any ab, so that a squared plus b squared is 1, that's again a Gaussian variable. And if a is close to 1, that's close to x. Okay, so that's a slight perturbation. So the other thing that you can do is you take a small fraction of the edges and replace them by independent copies. Okay, random fraction of the edges.
Okay, that's easier.
Yeah, so that's yes. But in the Gaussian setting, these little flows, physicists have been using this, but in the computer science setting, it's more replacing by little independent copies. Okay, so that's it, and here are the preprints. This is the old paper, and this is the paper, and this is the paper of Inger and Damron. Okay, so thanks.